Okay, so what we'll look at today is logic instructions. Now, in terms of logic, you've got to think of it in terms of binary. Okay, so we have some operations here, ands, ors. You know the truth table, so I'm not going to bore you with that. But how do you do them in terms of assembly language? Well, we've got move instruction, so we put an A into AA into there, and then we AND it with that. Now, it's a 3 operand instruction. So we're ANDing what's in R0 with F0 and putting the answer in A0. Now, when we look at this is really important. You've got to think of it as a bit level operation. All right. Now, so what's in R0? Well, there's AA. Okay, that's AA there, and there's F0 here. So when we AND that together, you AND anything with a 0, what do you get? You get 0. And anything with a 1, you're ANDing this with a 1 here. Yeah, you get the same thing back. So remember, A and 1 equals A and 0 equals 0. So what can you do with an AND? Well, it's very good for what's called masking out. So if we're not interested in these bits here, AND them with a 0, and we just get rid of them. Okay, so that's where that becomes useful. Okay, now the OR operation, there's 2 R's in OR. It's the same thing again, so we've got AA here and F0 here. So you this time remember A or 0 equals A, but A or 1 equals 1. So looking at this one here, these 4 bits here are being ORed with a 0, so we end up with the same thing back. ORing these bits with a 1, we get a 1. Now, so what we can use it for, we can use ANDs. ANDs are good for getting a 0, or is getting a 1. All right, so we can force. Now, so we've got the exclusive OR as well there, the EOR. Now, I'm not even going to look at that. And we've got the NOT as well. So that just reverses all the bits. Now, a lot of people find these exercises quite difficult. Now, these are based upon, and some of these are old exam questions. So the first one, and I'm just going to quickly go through and give you some help with these. But before that, let me just load up the example. So let's load logic. Okay, so I'm just going to quickly go through that, but again, you really need to think about it in terms of binary rather than so we're putting AA into R0. Now let me just put this back into hex so you can makes a bit more sense now. So we're ANDing it with F0. So what that's going to do is that's going to become a 0, and that's going to stay the same. All right, so there we go. Now we're going to put AA back in again, and then we're going to OR it with F0. So that's going to become a 1, and that's going to say 0A this time. No, sorry, I got that run the wrong way. FA, because that's going to cause a 1, and that's going to keep it the same. Sorry, I got that wrong. And then the exclusive OR is going to be doing that. And then finally the NOTing. Remember, it did all 32 bits that time. Right, so that's how it can work. Now, the logic exercises. So what it's saying is on this one then, write an assembly language program that converts an uppercase ASCII code in R0 for a letter, and then uses the logical OR operation to convert it to lowercase. Now, this is obviously when they designed the ASCII codes, they didn't just do any old numbers here. So there's capital A. We know that that is 65 in denary. Lowercase a is more than that, he says. Getting his phone out to work it out. I don't want to get it wrong, so shift bin. So this is 0, 1, 1, 0, 0, 0, 1, and I should use my calculator, 97. Okay, I'm sure you all knew that anyway. Right. Right, so that's right, 61 in hex. Now this applies to every uppercase and lower. The only difference is these two bits, well, these bits here. So if he was talking about it in bits, 1, 2, 3, 4, 5. Bit 5 is different. So if you just flip that bit from one to another to get from lower, we need to just change that bit, this bit here that I've highlighted here, but leave all the others the same. Okay? So this bit here goes from a 0 to a 1, but I want to leave all the others. So you have to think of a number, think of it in terms of binary, that I'm then going to go from a 0 to a 1. So what I'm going to use an OR operation to do that. Now it does say there use an OR. Okay, so that's all we're doing. All right. So when you see 2 upper and 2 lower in C#, that's all it's doing really. It's flipping that for ASCII codes, and I'm sure it's the same for Unicode as well. It's just flipping that bit. Okay. Now, so again, this one is doing the same, lower case to upper. Now this time we're changing this bit here, and so we're just basically going the other way. So this bit here is changing from a 1 to a 0. So we're going from lowercase to uppercase there, and this time we're using an AND. All right. Now I've kind of given the game away there on what you would need to do in order to do that. So kind of regretting that, but anyway, I've left it there anyway, so you can use that if you want to. Now number 3. This is a hard one. A process can only begin if bit 0, the least significant bit, and bit 4 of a register is set to 1, and bits 2 and 3 are set to 0. Now there's more than one way of doing this, but essentially this is the method that I use. All right. So what they're saying is we've got to test this register and see if bit 4 is a 1, bit 3 is a 0, bit 2 is a 0, and bit 0 is a 1. We don't care about 7, 6, and 5. They can be any old numbers. We don't care. Now, in order to do that, what we do is we put a 1 under the bits that we know have a set value. All right, and a 0 under the bits that we don't care about. All right. Then we AND. That's supposed to be an AND there. I don't know what happened to that. We then AND the valid number here. This is the valid number here with the mask. Now the mask is, I did mention, but mask is the one where we put a 0 under the ones we don't care about, 1s under the bits that we do. So that's called a mask. 1D in hex, that is, if you're worried about that. So we use any valid number we like. We know that this is a valid number because that can be any value, that can be any value, that can be any value. That must be a 1, that must be a 0, that must be a 0, and that must be a 1. Sorry, that can be anything, and that has to be a 1. Now, when we AND our mask with a valid number, we should always get that. All right. So just to prove it to you, well, let's just change. So say this bit doesn't matter. So I'm going to change that to, what was it? There's a 1. So let's change it to a 0. And something with a 0. We still get 0. So we still get the same answer there. All right. But if one of the numbers I was interested in, so let's say that this number here, this 1, is that, okay, so that's no longer a valid number. I AND it with my mask, and what do I get? Well, that no longer is this number here. So I get 1 now, as opposed to, what is that, 1, 2, 4, 8, 16, 17, or 11 in hex. So that's how you do that, right? Now, so just in summary then, what we're saying is if you add a valid number with this mask here, okay, you would always get that number here. If you don't get that number, then the number that you've got couldn't have been a valid number. All right, so that's what you need to do there. So basically you need to have a branch where you branch if it's a success or a failure. All right, okay, good question. That's a classic old exam one. Now this is a good question as well. Now again, what we've got, this is again simulating what is really going on when you do convert.toInt32. .toInt32. All right. So when you enter 26 on the keyboard, it's really the ASCII code for 2 and the ASCII code for 6. And what we have to do is convert that into 26 in binary. So what we've got is the ASCII code for 2 and the ASCII code for 6. Now, how do we do that? Well, here's another example. All right, so we have the ASCII code for 9 here, the ASCII code for 7. Now, if you remember, these 4 bits here are the actual values that the ASCII code represents. So there's 9, but that's the whole ASCII code there. There's the ASCII code for 7. Okay, here, but there you can see 7. So what we can do is mask out those bits. We want to convert these to 0. We use an AND for that. So then we end up with the value 9 and the value 7. Okay. Now in the case of 26, we want to multiply this one by 10 to get 20, and then add it to the 6, and then we end up with 26. So this would be sort of simulating what convert.toInt32 would do. Okay. So that is the logic instructions. All right. Now this is where the questions do get a little bit harder. Requires a little bit of thought, but it's not too bad. All right, there we go. So there's logic done.